Hello everyone, and today we're going to be going over the problem construct binary tree from pre-order and in-order traversal from week 2 of the June Decoding Challenge. So in this problem, you are given two arrays, one representing the values outputted with an in-order traversal of the binary tree and one of the values outputted using a pre-order traversal of the binary tree. So essentially what in-order traversal is, let me just delete this. What an in-order traversal is that you just visit all the nodes starting from the left to the right. So, for example, if the binary tree looked like this, um, you'd visit this one, then this one, then this one, then this one, etc. Because this is still a little bit to the left of this one, and yeah, so essentially it's like a scan from left to right of the nodes. And a pre-order one is just one that um, like goes all the way down the left, so it'll uh, print this value out, then it'll print this value out, then it'll print this value out, then this one, and then it'll come back here, and then it'll print this one. So it'll go print out the value of the current node, and then go left, and then print out that one, and then go left, and then after it finishes going left, then it starts going right from the nodes that it came from. And yeah, that's just a quick explanation of it. Like, um, there's probably a lot of explanations about this on Google, so you can just search that up if you need to. And so uh, you're basically supposed to construct the binary tree given these traversals, like what they output. And yeah, so a disclaimer before going into my solution. This is not the official solution. The solution's quite slow, but it still works because it's just the first thing I thought of that would work given these constraints of how many nodes can be inside the tree, and it still works. So yeah, that's just a disclaimer. Yeah, it's not the official solution, but it's just an easy one to think about that I came up with. So uh, the first thing to figure out is that the important thing when adding a number is to find the node which to attach it to. So if our tree looked like this, and we want to, and we've moved through like some numbers in the array, when we run into the next number, we need to know which node to attach it to. Because if we can figure out, yeah, we need to attach it to the left of this node, then we can simply attach it, right? So we can use the in-order traversal to help us do this. So if we are adding a number from the pre-order array, let's just say like what, so this is like 3 9 20, 3 9 20, well, we don't even need to go that far, so let's just say 3, and the in order one is like 9 3 whatever. So we know that uh the number just after 3, um like if we go in order of the pre-order traversal, the new number after 3 has to be attached to some node that's already in the tree. In this case, there's only one node in the tree, so we know it has to be attached to this 3. But let's just say we run into 20. Well, the 20 could either be to the left of 9 or to the right of 3. Either one would work for the preorder, but we just know that whatever new node we run across in the preorder traversal, it must be attached to some node already in the tree because we came from that. So that's one useful thing to know. And so using that information, when we let's just say this is 3, so when we want to add 9 to it, we can check the in-order traversal to see if 9 is to the left or to the right of 3. In this case, because we know 9 is to the left of 3, we can add 9 to the left of 3, and we know 9 is attached to 3 because we are trying to add it in the preorder. Next, we want to try to attach 20. So we know 20 is attached to either 3 or 9. So first, we can check whether 20 should be to the left of 3 or to the right of 3. In this case, in the in-order traversal, 20 is to the left, to the right of 3. So we can just attach 20 to the right of 3 because there's nothing attached there. But if, say, 20 was on the left of 3, uh, if 20 was on the left of 3, um, then we would know that 20 must be attached to a node to the left of 3. So we can't attach anything to the left of 3, so we go to 9. So now we check if 20 should be attached to the left or to the right of 9. And in this case, we see that 20 is to the right of 9. But since there's nothing to the right of 9, we know 20 should be attached there. So we can repeat this process to attach every single node in our preorder traversal. So if we go through the preorder traversal, I'll just do this as the test case, just to illustrate what I mean really quickly. This shouldn't take that long. So our algorithm would run something like this. So we would want to go through this preorder traversal, and we want to attach all the nodes. So first 3, of course we know that's the root because that's the first thing that the preorder traversal visits. Then we want to attach 9. We look at 3, we find that 9 is to the left of 3, and we know that 9 must be attached to 3, so we can attach 9 to the left of 3. And we know it's to the left of 3 because it is to the left of 3 inside of our in-order traversal. Then we go to 20. We know 20 must be attached to either 3 or 9. And since we see that 20 is to the right of 3, and 3 has nothing to the right of it, we know that it must be the one attached to the right of 3. Next, we try to add 15. We know 15 is attached to either 3, 9, or 20. And since 15 is to the right of 3, we and there's already something attached to the right of 3, we move over here. Now we check whether 15 is to the right or left of 20. And since 15 is to the left of 20, and there's nothing there, we know 15 must be attached to the left of 20. And same thing, but with the 7. So we start from 3, we figured out that it's to the right, then we know it's to the right again, because 7 is to the right of 20. There's nothing there, so we would attach 7. So basically, we would just keep on going and figure out which spot we need to attach our current number in to match the rest of our tree. So that's exactly what we do. So in our implementation, I just have a map to make it really easy to figure out whether a number is to the left or to the right of another number. Because it says all of these consist of unique values, this is a legitimate strategy. So I just put the number inside of this in order and the index. So if I want to figure out if 20 is to the right or left of 3, I can simply look at the map to see which index 3 is at, and look at the map to see which index 20 is at. That way I can instantly get the indexes and compare which one is to the left or to the right. And so we do the same thing here with this pre-array, even though I don't know why I did that, actually. Yeah, I honestly have no idea why I did that. I don't think it's needed because I don't think I used it once. Yeah, let me just delete that. Kind of pointless. Yeah, so we first make this map here, so we can easily compare whether a number is to the left or right of number inside of the in-order array. Next, we know the first number in the preorder array has to be the overall root. So then for every node we need to add inside of our preorder array, so we're iterating through starting from 1 because we know we want to add 9 and then 20. So we start from the overall root, and we set a boolean. This is essentially a flag saying whether or not we can add the thing to the right or to the left, because as you know, if we're 3 and we want to add something to the right, if there's already something to the right, we can't just add it because there's already 20 to the right. So we need to move to 20 to then check whether we attach it to the left or right of 20. So we set move to false, and if basically this is to the left of the overall root, and there's something there. So, for example, if we want to attach something here, we know it's to the left of 3, but there's something there. So we move to this to figure out whether or not we can attach it to this. Then we move to our node here, which starts from the overall root, to the left, and we set it to true. And otherwise, we move to the right and set that to true. And this essentially will traverse the tree over to find the node which we need to attach our new node to by moving left, then moving right, because, or whatever it needs to move, right? Like left, right, or right, left, doesn't really matter, because what it does is it compares which index the current value is at to the index of the value we want to add. So we know if we can look at any node and know if we need to go to the left or to the right. So after that, we know we should attach it to this node, which is t. So we can just do a simple check of whether it's to the left or to the right in the in-order traversal. And if it's to the left, we attach it to the left of t, which we've moved to the right node, and otherwise we attach it to the right. And at the end, we return the overall root, which will be the root of this newly constructed tree. So if we run this here, this should be accepted. And yeah, so it's accepted, but it is a little slow, because since we start at the overall root every single time. So yeah, but at any rate, that's a solution to the construct binary tree from preorder and in-order traversal problem. Thank you very much for watching. I hope you guys enjoyed the video, and I'll see you guys in the next one.